next is Takahiro Haruyama presenting his work on UEFI Bootkit hunting. Even if you aren't interested in UEFI, the techniques that he uses for code search are really applicable to all sorts of problems. So we think you'll find this really interesting. So welcome, Takahiro.
Thanks for introduction. I'm Takahiro Haruyama, security researcher from Binary. Today, I talk about our bootkit hunting research. This research was not done by me alone, supported by our research team members, including Fabio, he's here, Yeager, Anton, Sam, and Alex. This is today's overview, except the background and the conclusion. The main content has 3 parts. First, we decide our hunting approach based on non-bootkit analysis. Second, make the hunting rules and share the result. Third, introduce more advanced methods than Yara. I have many slides in 30 minutes. So for some slides, I will only give a summary. First, I explain the background. A bootkit is a type of rootkit running before OS boot. Once installed, it's harder to detect than OS-level malware and can bypass all OS security mechanisms like patchguard, then enable to run arbitrary kernel code. That's why it's attractive for attackers. Multiple UEFI bootkits have been discovered in the world over years. As a trend, the infection target has moved from spy flash memory to EFI system partition due to hardware-based security features such as Intel BootGuard, BIOS Guard. But the risk of bootkit infection still exists because UEFI Secure Boot can be disabled through physical access, vulnerability exploits, or supply chain attacks. And additionally, not only Windows targeting, but also Linux targeting bootkit POCs have been discovered lately. We expected there might be more. That's why we started this research to discover unknown bootkits. What we did first in this research was to extract generic code patterns by analyzing known bootkits. We analyzed 6 bootkits: Lojax, MosaicRegressor, MoonBounce, CosmicStrand, ESPecter, and BlackLotus. Mostly, they are doxy drivers and bootloaders. From the next slides, we share our findings extracted from 3 different perspectives: bootkit hook chain, additional components and features, and OS persistence. Bootkits hook multiple code locations to execute their code in operating system. Lojax and MosaicRegressor set a create event callback, and other bootkits use 2 types of hooks. One is boot service function table hook. The other is inline code hook of some bootloaders and kernel functions. However, as generic code patterns, create event callback is too common, so it will make a lot of false positives. Also, boot service function table hook detection, focusing on the function pointer replacement, is only effective for one bootkit. Inline hook detection was likely the most promising. For example, 4 bootkits hook the same function, OSL arc transfer to kernel. But the generic detection was hard. The inline hook usually has 2 steps: memory scanning with code signatures and code patching. Each bootkit has a different memory scan algorithm and patched instructions. So there was nothing in common. Some bootkits have additional features to avoid detection, but finding generic patterns was also difficult because they were too common or inline hooks. For OS persistence techniques, Lojax and MosaicRegressor install an executable in NTFS file system directory, but the code sequence is common in file system drivers, and the file path can be obfuscated. On the other hand, other bootkits have good unique code for generic detection. They clear write protect bit in CR0 register and parse multiple PE format structures like shellcode. Why the behavior is good for detection? Because bootkits often remove write protection on read-only memory pages to set inline hook code or modify PE header values such as entry point and section permission. This behavior is rare in UEFI applications. Also, shellcode like PE parsing must be rare in UEFI modules and applications. Specifically, we focused on 2 structures: image export directory and image-based relocation. In this way, we decided to detect these OS persistence techniques. Based on the generic code pattern extraction, we created the detection rules and got some results. As threat hunting data sources, we used BlackLotus and our binary risk hunt platform. So we created YARA and firmware hunt rules. The workflow is simple. First, detect suspicious samples using the rules. Second, analyze the samples using IDA. If there are false positives, refine the rule and rescan. If not, analyze the details. In this section, we show the YARA rules and hunting results only because most people use BlackLotus and the binary risk hunt result was covered by BlackLotus. Other advanced detection methods, including firmware hunt, will be introduced in the next section. The first rule detects the clearing of the WP bit in CR0. It was created from the code of MoonBounce, CosmicStrand, and ESPecter. As we can see, the code sequence to read and write CR0 is very simple. So I had to exclude false positives in some EDK2 modules and commercial bootloaders. Using this rule, we discovered 2 bootlicker samples. Bootlicker is an open source bootkit based on DMA backdoor boot. The samples were detected by 1 or 2 antivirus engines on BlackLotus, but not as bootkits. The hook chain is the same as bootlicker. One sample has no user mode payload. Another downloads shellcode from local IP. So we think they were just POCs under development. By the way, another open source bootkit, EFI Guard, also clears WP bit in CR0. But the previous rule was not effective because the code calls ASM write CR0 function with the bit mask value as an argument. So we created another rule to detect clearing the CET, control flow enforcement technology bit in CR4 that is implemented in EFI Guard. It's specific to EFI Guard, but it's worth creating it because EFI Guard is abused in the wild very actively. As a result, we found 2 samples named Vixen EFI with 0 detections. So we compare the samples with the EFI Guard doxy binary built from the source, but the differences were trivial. And normally, the detection number of EFI Guard is around 10 to 20, so they should be detected as well. And we tried to identify the purpose of the binary, but we could not. Guessing from the file name, it may indicate game cheat software, but we are not sure. The third rule detects code resolving kernel API address. The code accesses multiple structure offsets of image export directory, like this. So I translated the structure offset accesses into one code sequence using yellow jumps. This rule was created from MoonBounce, CosmicStrand, and ESPecter. After the hunting, we discovered 2 unknown bootkit samples, including an ASCII at Valkyrie, to output in a debug mode. It was a UMAP-based bootkit, but more practical implementation. For example, JSON configuration file, custom FNV string hash algorithm, more code signatures for inline hooking, and so on. Other than that, the most behavior, including the hook chain, is the same. Then we identified the loader, kernel driver sample loaded by the bootkit. It uses the same string hash algorithm, and the data and the strings are highly obfuscated. We decoded one of the strings. It was an IP address resolved as Valkyrie CX. According to the website, the bootkit was part of game cheat software, and they say it has never been detected. The next rule is detection of resolving code relocations. Unlike the previous rule, we could not create one code sequence because the code order was not fixed across the bootkit samples. There are 2 patterns for each instruction bytes when accessing image data directory and image-based relocation. This rule was created from MoonBounce and BlackLotus. Using this rule, we found 4 additional UMAP samples. One of them was not detected at all, but the code was the same as the binary downloaded from the GitHub release page. Other samples have different hook chain from UMAP, but we concluded they were likely another game cheat software. after checking the compressed parent binary from VirusTotal. By the way, we also discovered one unknown sample named Bootkit UEFI. It was detected as Bootkit already, but last month, the detection number dropped sharply from 6 to 2 on VirusTotal. It's weird, so I got interested. It was Bootkit disabling PatchGuard and DSE, driver signature enforcement, like EFI guard, but the code is not similar. And the hook chain is also unique. However, after an additional retro hunt, we found another variant, and based on the related binaries, we recognized it was game cheat software too. And my coworker pointed out there is another type of bootkit running in PEI phase. Unlike later stage bootkits, it has no OS persistence code, but similar one, resolving relocations of the infected image. Using this rule, we found another backdoor created by the same author, but no other samples were found. This is the result summary. We discovered 12 bootkit samples in total, and among them, 10 were not detected as bootkits, and 4 had 0 detections. Every sample, except Bootkit UEFI, reused open source code, Bootlicker, EFI guard, and UMAP. Unlike other open source bootkits, UMAP was not detected even though the code was the same. I think it should be detected like DMA backdoor boot and EFI guard. And I learned bootkits are mostly used for game cheating, not malware. Game cheat software is everywhere. And except the game cheat software, we could not determine if the samples or improved variants were actually used by threat actors. It's a limitation of VirusTotal without context. But at least we could check the efficacy of our generic detections. So we hope other vendors will improve their visibility against bootkits using our findings. In this section, we cover more advanced methods than Yara. We introduced the Yara rules for generic bootkit detection, but the rules have some limitations, such as detection accuracy and rule readability, because they consist only of code byte sequences. So we explored more advanced detection perspectives using code analysis, semantic information, machine learning, and differential firmware analysis. As I said earlier, Yara is not effective to detect code clearing WP bit in CR0 when the bit mask values are passed as the function argument. So for the detection, we developed a static analysis POC using IDPython. Specifically, the script first detects ASM write CR0 function, then identifies the code range between clearing and setting WP bit. And within the code range, it finds memcpy write call, like internal mem copy mem or qmem copy, and so on. Then if found, it validates whether the copy size of the third argument matches the total size of the decoded instructions in the source pointer of the second argument. We scanned over 500 samples with ASM-write CR0 function, but no FP was found. Another perspective is semantic detection. Our free tool, Firmware Hunt, enables to create detection rules based on UEFI, GUID, protocol, NVLAN variables, and so on. For example, when writing a YARA rule for clearing WP bits in CR0, we need to exclude false positives, so define the code sequences for exclusion. But in Firmware Hunt, we can use semantic information for that purpose. This makes the rule much simpler to understand and easier to maintain. We also utilize the semantic information for sample clustering, like imp fuzzy technique in Windows malware analysis. To create clusters, first, extract semantic information using Firmware Hunt. Second, calculate the TLSH fuzzy hash value of the information. TLSH means trend micro locality sensitive hash. For example, GUID and protocol service names are concatenated into one string in address order, then the TLSH value is calculated. After that, create clusters using scikit-learn's DB-scan algorithm based on the distance calculated by TLSH values. By using semantic information, we can categorize UEFI binaries very accurately. It's useful for suspicious sample triage. For example, we got one unknown sample from VirusTotal, and the detection rate was 0. So we needed to analyze it. To quickly check the similarities with already analyzed samples, we create clusters including the sample. This is the result visualized by MDS, multidimensional scaling. As you can see, the target sample belongs to cluster 7, UMAP variance cluster, and the closest sample is Valkyrie. So we can compare the functions with the sample quickly, for example, using bindiff or diaphora. Semantic-based detection works well for most cases, but infection type bootkits may require detailed analysis for detection because the code is small and has no additional semantic information. To resolve this issue, we propose anomaly detection based on differential firmware analysis. We support multiple change detections in module, semantic information, and function levels. Specifically, similarity of the same modules in current and previous firmware is mainly detected by function diffing. I mean, percent of matched duplicated functions based on locality sensitive hash. And if any change is detected, we additionally run generic detections, such as UEFI service table function hook detection and embedded executable detection, and so on. as a use case, we detect MoonBounce infection. First, the module change is detected by the file hash. Second, the module function similarity is calculated. Finally, detect the embedded kernel driver in the bootkit. In this way, our anomaly detection can catch a small but malicious change based on differential analysis. I wrap up my presentation. Bootkit detection is still immature. Our generic detection approach was effective in hunting previously undetected bootkits. And we also introduced advanced detection techniques. For future work, we will create more generic detection indicators from different perspectives. And we have never seen ARM-based bootkits, so we may try to find it or create it. Last but not least, for this research, I appreciate the help of some researchers. Martin and Anton from ESET and Alexander from Sentinel-1, they shared their telemetry analysis results. And Brian from Carbon Black, now part of Broadcom, he shared more samples for this research. Thank you so much all. That's it.
All right, I think we have time for a question, maybe two. Any questions?
Hello, thanks for your talk. I was wondering for the bootkits that rely on some loader or some installer to execute first before writing to the EFI system partition. Did you consider looking at characteristics of those installers or loaders as well as of the bootkits themselves?
You mean the loader is bootkit installer, right?
Yeah, the bootkit installer.
We didn't analyze the bootkit installers.
Okay, so just the main bootkit files that you would find, for example, in the EFI partition.
Yeah, I think a few years ago, I researched bootkit installers in my previous company.
Okay,
Yeah.
I'll look you up again then.
VMware blog, please check it.
Thank you.